Everyone, welcome back to the Linux. Today we are going to see about single layer perceptron. The single layer perceptron is in a supervised learning and used for a classification task. The main inspiration of in a single layer perceptron is in a biological neurons in our human heads. In general, there are trillions of neurons in our brain and each are connected to each other. For example, let's take in a three neurons and each are connected to each other, and each neurons get the signal from the others, and it will process the signal, and it will decide whether we can pass to any other neurons or we can simply not. This is in a concept of our brain will work, our neuron will works. This basic concept we will apply on the single layer perceptron in machine learning. Assumption of perceptrons. Single layer perceptrons. The data is linearly separable. There is a linear relationship between the inputs and the labels, and also the labels are binary, either in a +1 or -1. The futures are numerics. The inputs are always the numbers in the numerics, and it will converge if the data is linearly separable. Let's take let's take an input. These are the inputs. Let's take x1, x2, x3, and it will process. We will give this input to in a perceptron, or we can say as neutron. Let's take perceptron. The perceptrons will sum it will multiply the weight and to a corresponding inputs and sum them up and return the value as set. The equation it will looks like, for this case, w1 x1, w2 x2, and w3 x3. The number of bits will increases as per the number of inputs, and there is base b. This is the equation looks like for an perceptron. Usually during the training process, we will adjust the weights. We will adjust this w1, w2, w3 to minimize the errors between the data. And this is our input. Whenever these inputs come, it simply find the value of z by multiplying its weight to in a corresponding inputs and sum them up. It returns the value as in a z. After we found the z, we simply pass the value into some active function. It will tells about the data belongs to our perceptron or not, or it will tell which the that it will tells the data which class it belongs to. For example, there is a function called an assign function. It will simply tells if it's written 1 if z is greater than 0, and it is written -1 if z is lesser than 0. The 1 is in a predictor and -1 is also in a predictor. These are the classes which is representing this inputs. How it will works during the training process. We initially assign the weights. Basically, we will assign the values in zeros or some random value. And for each iteration, for example, let's take in a thousands of data sets. On each iteration, we simply compute the process. The w1 x1 here it is in a number of input is one. Number of input is one. So this equation looks like w into x plus b. If the number of there can be a many number of inputs like w1 x1 plus w2 x2 dot wn xn plus b. the n represent the number of futures in the inputs. And I have already told that the sine function simply return the +1 if z is greater than 0, and simply return -1 if z is lesser than 0. Here it is same. It will if the z is greater than 0, it will simply return the +1. Here y bar is the predicted value. Predicted value. I erase this. And y is the actual input. After the z will found out after using this equation, we will found the z, and we will simply pass to this sine function. If z is greater than 0, then it will return 1. If z is lesser than 0, it will return -1. This one and -1 is the predicted value, and there is an actual input we will give in the training data set because it's a supervised learning, right? So it will compare this predicted value to an actual input. If doesn't match, if it's not match, we will update the w and base using this formula. If it is matched, we simply skip the skip the iteration to next one, and we will repeat this until there is no misclassification or maximum approach. The approach is nothing but if you travel the entire data set once, it's called as a one approach, and if you travel the entire data set two, it's called as two approach. We will define the predefined approach for a training data set, or we can there is no misclassifications. If you travel the entire data set, there is no misclassification is found, then we can say that our perceptrons found the correct weights for any inputs. There is a loss function during the training process. If the data is misclassified, if the actual prediction and the prediction by any model it's not same, before we will update the weight using this loss function. Basically, we will this is a loss function. We already used, sorry, let's erase this. We first found the value of z. For simplicity, we can take the input as 1. Let's take z equal to 10, and the actual prediction value for the input x1 is -1. But for our model, it will give 10. So the sine function will return as +1. So we can see that there is +1 not equal to a -1. So there is a misclassification here. So we need to update it, right? So we use the loss function. The loss function will, this is an actual prediction value. This is -1, and it will return the 10, right? We will pass this 10 to a sine function. We will pass this 10 to a sine function, and sine function return +1, right? Actually, this equation looks like minus my minus of -1. This -1 is nothing but the actual value, sorry, actual prediction provided in the data set, and this one y w into x plus b, we will found the value as 10 and pass into in a sine function, and it return as +1. And here we can say that after 0 comma, after we calculating, it will looks like the +1 minus into minus cancel and come as 1. Then maximum between the 0 and 1 is 1. 0 and 1. If the loss function is greater than 0, here we can see It will come in the upcoming time. The loss function is greater than 0, then we will update it. If the greater than or equal to 0, we will update it. If the loss function is lesser than 0, we don't update it. So here the loss function is greater than 0, then we will update using this formula. The loss function is greater than 0, so we update using this formula. If the loss function is lesser than 0, then we not update it. Here we can see that update occurs only when the loss is greater than 0. Here the simple dry run, how the model will train and how it will update its weights and base. This is let's take this in a sample data set, and initially we assign the weight as 0 and base is 0, and this n is nothing but is in a learning rate. Usually it's range from 0 to 1 to 0.1 to 1. Here we take as 1. In first epoch, the equation will looks like z equal to w1 x1 plus w2 x2 plus b. Initially we found that x1 and x2 are the inputs, that is 2 2, and w1 w2 are the base, it's also 0 0, it's an initial weight, and base is also 0. If you substitute this in this equation, it's like 0 into 0 plus 0 into 0 plus 0, it will return as 0. Z is 0. If the z is greater than or equal to 0, it's simply there is in a formula. If z is 0, then it's there is no sign, right? If z is greater than 1, sorry, if z is greater than 0, it will return positive 1. If z is lesser than 0, it will return as negative 1. So if z is equal to 0, it's considered as in a misclassified. So we just update the weights so that I there is a formula. I have already told that. Here it's a formula. We update based on this. It looks like W equal to W volt plus n into yx. The volt is 0 comma 0 plus 1 into the actual prediction. Here it is a actual prediction is plus 1. So 1 into plus 1. This y is an actual prediction, and the x is 2 comma 2. This one is multiple all the 2's, and this one is also multiple these 2's. The answer will looks like 0 comma 0 plus 2 comma 2. If you add them up, it will become 2 comma 2. These are W, and for any bias there is a formula. Volt B plus n into y. B equal to B of volt plus learning rate into y prediction. The volt B is 0 and learning rate is 1 into y prediction is plus 1. So base equal to 1. So the after the first epoch, after the first dataset, the W become 2 comma 2 are the weights, and base become 1. Here you can see that. And let's go for a next iteration. When the inputs like x1 equal to 1 and x2 equal to minus 1, and we have updated the weight x sorry w1 is 2 and w2 is 2 and base is 1. Then we substitute in the equation z equal to w1 x1 plus w2 x2 plus b. Then substitute the value in the equation is 1 into 2 plus minus 1 into 2 plus 1. It's 2 minus 2 plus 1 z, and it will return as z equal to 1. So z is 1, right? So if you pass the z into sine function, of course it's written positive 1 because that is greater than 0, and it will return as positive 1. Here we can see that it's a predicted value, right? It's a predicted value. It's defined it's class 1, and you can see that in actual prediction the y2 is minus 1. So plus 1, it's not equal to minus 1. So there is a misclassification here. So we need to update it. So we need to update it. We will use the same formula. Here it is. We use this formula. I will do that. W equal to old W plus n into y into x. Old W is 2 comma 2 and n is 1. Actual prediction is minus 1 and x is plus 1. And sorry, and the x is 1 comma minus 1. If you multiply the minus 1 into this, the signs are reversed. And if then multiply the 1, it remains same. So minus 1 plus 1. And if you sum them up, it will 1 comma 3. The new weight is 1 comma 3. And similarly, we do for a base. Base equal to old base plus learning rate into prediction. The old base is 1. The learning rate is 1. And actual prediction is minus 1. And it will 1 minus 1. The base equal to 0. So the new base is 0 and the new weight is 1 comma 3. And we will do similarly for an example 3, that is we similarly substitute in the x1, we similarly substitute in the z equation, that is w1 x1 plus w2 x2 plus b. It will simply written as minus 7, z equal to minus 7, and we will pass into a sine function. So of course it will return minus 1, and this is a prediction value by the model, and this is an actual input. Here we can see that they are same. So it is classified correctly. So we don't need to update the W and base B. We just skip it. We just skip the updation because the prediction value, sorry, the actual prediction and the prediction value by the models are same. So we just skip the update. On the epoche 2, we found the same. We will do the same operation for a same operation using this same data set, and if there is any misclassification, we will update it. But in the second epoche, let's for the input like x1, input like the x1 is 2 and x2 is 2, x2 also 2, and we already know the updated weight, that is w1 and w2, both w1 is 1 and w2 is 3 and base is 0. If I calculate the z, that is 8, and I will pass into in a sine function. Of course it will return plus 1. So it is in a plus 1 is predicted by the model, and I will see in the actual prediction in the data set, it's also plus 1. So both are same. We just simply skip it. And similarly, we do for an example 2, and it will also actual prediction and the actual prediction and the prediction by the models are correct, and it's also correct for an example C. So in the second approach, we can see that there is no misclassification in the dataset. This means we found the optimal weight and the optimal base. So there is no misclassification. We don't update the weights and the base. So this means we found the optimal weights and the base. So we will stop the iterations here itself. If there is no weight is there is a weight is updated in the each epoche, we will stop the iteration in predefined epoche like thousands and 10,000s like that. And sample predictions dry run. We know that we will update the weights and the base on the training data sets, and we will store the weights in the model. After the model is trained, we will predict the values on the unseen or new data. In the After the model predict, we found that weight is 1 comma 3 and base is 0. For a new prediction point, for example, let's take the input as 1 comma 1. If you substitute in the z equal to w1 x1 plus w2 x2, here the w's are constant during the prediction, so we can simply write as z equal to 1 into x1 plus 3 into x2 plus 0. So 0 is nothing but we simply skip it. The z is look like x1 plus 3 into x2. So substitute the input to z, it looks like 1 plus 3, that is 4. So of course the sine function written plus 1, it is classified as plus 1 as a prediction. And for the second input like 0 comma minus 1, it similarly do the calculations, and it will found the value as in a minus 3, and it will simply pass to in a sine function. It will return as minus 1. This minus 1 it's considered as in a prediction. And similarly we do for another examples like x equal to 2 comma minus 1 and one more examples. This is how we predict the unseen data after the model is trained. The real world examples are applications of an SL sorry single layer perceptrons. We will use for an spam detections and credit card frauds. And there is one more thing. The single layer perceptron is in a fundamental or in a base layer for a neural networks. In single layer perceptrons, there is one layer. There is one layer. The inputs, sorry, there is each class have a one perceptrons, and we will train them up separately, and we will calculate them based on the input. Whenever the inputs like x, it will pass to all classes, and it will tell them which class it belongs to. And it is only one layer in the single layer perceptrons. It is the base of in a neural networks, because in the neural networks there is a n layers of perceptrons, or we can say as n layer of neurons. And that's it from this video. Let's see you on the next video. Thank you.